start with an announcement.
Okay. Hi everyone, I'm Cindy. I'm the president of Women in Computing.
I'm Desiree, and I'm the computer engineering representative.
Yeah. So we're here today because we have an event tomorrow called Pizza with Professors. Joe's actually going to be there, and it's a super casual panel style event where there's time to mingle before and after, get to know your classmates. But this is a great chance to ask the professors anything you want to ask them. It could be personal questions like, did you get to see us for the money, or did you actually like it? Or it could be, more academic questions like, how can I secure that A in your class? But just really anything you want. And of course, this is a great chance to make some friends in the class because you never know, if they're going to be your next partner, your next coworker, your next manager. But yeah, this event is going to be tomorrow, 4 to 5. In Web 2250, and if you want to submit a question, you can actually scan the QR code right here. We'll also leave a poster on this chair right here. But if you scan the QR code and you stay till the end of the event, you'll be entered to win a Target gift card. Yeah, so exciting. So you guys all know where Catmull is, right? Catmull Gallery. Okay, if you don't, it's the top floor of Web where, you can actually see sunlight. But I will be there like 10 minutes before the event in case anyone's lost or in case you don't want to walk in by yourself. I would love to get to know all of you more too, so we can go together. It'll be really fun. You can, make new friends, get an A in the class, know the professors, maybe walk out a little bit richer. So we all hope to see you there. Are there any questions?
So you can also go to our website at wic.utahclubs.org, and this is on there also. So that survey is there too.
Yeah, we hope to see you there. Thank you.
Okay, so no problem set this week because the midterm is on Thursday. Remember that last name starting with A through J, you want to go up to, is it 1250, I think? And the rest of you come down here. Matt did a review last week. The video from that is online in the usual place. I did a review last year of a different midterm. It's available. It's linked into the schedule here somewhere. Right down in here. There are 3 different old midterms, and their solutions are posted along with a list of topics that we have covered and will be covered, or potentially may be covered over the midterm. So lots of stuff to look at and review and study. Any questions I could answer? Yep.
Will the master theorem be provided on only the first page or on every page where we need it?
Now, the master theorem will be on the front cover sheet. Which reminds me, you can bring one sheet of notes. You can fill it in front and back, handwritten or printed out. Yes?
I'm just curious when you should expect P7 to fill up.
I'll get P7 out soon. I'll try to do it today. We'll see how far we get today. Yeah, problem set 7 will come out soon this week and be due next week like usual. Yeah.
If we look at the last problem set, the modular arithmetic, the very last problem.
Okay. Let's see. PS6-5. Okay.
The trick to figuring out.
Okay. So when you see something like that, there's always a trick, and we don't have very many tricks yet. Basically, the only trick we know for doing that at the moment is to use the theorem that says we can simplify the base of an exponent. Okay, substitution rule. So you could talk us through how to solve this. Yeah.
I think 135
Okay? So I'm going to repeat what he said. The thing you realize is, clearly, if this were 137, it's easy to see you take 137 mod 136 and get 1, and 1 to any power is 1, and 1 mod anything is 1. If that's 135, that's 1 less than the modulus. And the thing you realize about that is negative 1 and 135 are the same mod 136. They differ by 136. Any two things that differ by a multiple of 136 will be the same mod 136. So we can replace the 135 with a negative 1, and then simplify. And since we're taking it to an odd power, we'll get 135 to that odd power will be, negative 1 to that odd power will be negative 1. So the answer is negative 1 mod 136. And what is that? 135. You do ask the question. Okay. Any other questions? Okay. Well, we're sort of covering number theory and RSA encryption in a weird way, like one lecture a week. So let's get this strung out. So today we're going to continue that conversation. By the end of class, hopefully we'll get to sort of the definition of how RSA works. We'll have to loop back after the midterm, a week from today, to really put RSA in context of how it's really used. So let's start with where we left off last time. Which was modular exponentiation. So this is where we were last time. The idea is we've got x, y, and n, and x and y are between 0 and n. These are all integers, and we're trying to compute x to the y mod n. And we sort of looked at a couple of ways of doing it that didn't work out, mainly because if you're computing x to the y mod n, and all these numbers are n-digit integers, where n could be like 1,024 or 2,000 or something, massive, you just can't go and say, okay, I'm going to multiply x by itself y times. That's just too many multiplications. A 1,000-bit number can be as big as 2 to the 1,000, and that's just unimaginably huge. So it would take an incredible number of multiplications, and if you're not careful, if you did all the multiplications before you took the mod, you'd have an even more incredibly long number to take the modulus of. So what we came up with was this idea of repeated squaring as a way of computing, of doing an exponentiation. And we have on the left sort of the divide and conquer algorithm to do it. You can see that sometimes, depending on whether y is even or not, you either square or you square and multiply by x. And similarly, we have the iterative version, which again decides whether to either square or square and multiply by x. And then each time we do an operation, we take the result mod n. So we don't do all the squaring and multiplying and then take it mod n. We knock it down to size each time. That keeps the number from getting too big. Makes everything else more efficient. So let's try to remember how those algorithms work. Just by, unfortunately, I left my stylus in my office, so I'm going to try to draw with my mouse here. And to make it easier on us, we'll use small numbers, of course, and let's forget about doing the mods. Let's just do the multiplications. So, and squaring. So suppose we want to take 2 to the 5th power. Okay? So let's do the iterative version. That's sort of my favorite version of it. So let's take 2 to the 101 power. Okay? The way that algorithm works is you start with 1. And then you read the exponent from left to right, and each bit tells you what to do. So if you see a bit of 1, what do? It tells you what to do to this thing right here. So if you see a bit of 1, what was it you do? I couldn't hear that.
Multiply by 2.
No, we don't multiply by 2. Let's go back and look. So if we look at each bit. If the bit is 1, we square it and multiply by x. If the bit is otherwise, we just square it. So a bit of 1 tells you to square it and multiply by x. The other bit tells you to square it. So if we come back to where we were, we see a bit of 1. So we square this 1. 1 squared is 1, and multiply by x, which is 2. So that turns this number into 2. We square it and multiply by x. And then we look at the 0. So when you see a 0 bit, what do? You just square it. So that's 4. And then we see this 1 bit right here. Square it, giving us 16, and multiply by 2, giving you 32 as the answer, which is 2 to the 5th. Right? If we looked at 2 to the 8th, that's a power of 2. That would be 2 to the 1, 0, 0, 0. What's going to happen now? Again, scan the bits from left to right. We want to start with 1, of course. So you see the 1, so you square this 1 and multiply by 2. So that gives you 2. Then you're going to see 3 zeros. So what are you going to do for each 0? Just square, square, square. So we're going to square it, square it, square it. So we go from 2 to the 2nd, to the 4th, to the 8th as we square. So we'll go to 4, and then to 16, and then to 256. So it's just, we got the idea for the algorithm from the observation that we could easily compute powers of 2. I'm sorry, we could easily compute powers that were powers of 2, with the exponential power of 2, by repeated squaring. And we have to modify the repeated squaring idea a bit to deal with exponents that aren't powers of 2. Then the recursive algorithm, the divide and conquer algorithm, does the same thing. It's just written recursively instead of iteratively this way. And in the real algorithm, we would take the mod every time we had a chance. Now, the next caddis problem you're going to have for PS7, you can be implementing this algorithm on, but I'm not going to make you do it on big integers. You'll be doing it on longs. And I'll tell you a mistake students make all the time. The guarantee is that the modulus will be a 32-bit integer, meaning that you won't have to use, you never, as long as you do the mod after any operation, you won't ever overflow. So clearly, if you got to compute, the algorithm says to compute z squared, mod n, you would do the squaring and mod n. Students are having trouble with that. But what about the step that says x times z squared, mod n? Sorry about that. Now, how would you compute x times z squared mod n if I told you all the numbers are going to be representable as n's? Yep.
Z squared mod n times x mod n?
Right. You'd have to do the z squared and take that mod n, and then do the x and take that mod n, even though the pseudocode says something different. Because you got, the pseudocode is assuming that integers won't overflow. So you got to make sure that after each operation, whether it's a squaring or multiplication, you take the mod. You don't want to, if you do z squared times x, you could overflow before you get a chance to do the mod. So keep that in mind. Right? So there's that algorithm. Any questions I could answer about modular exponentiation? Okay. Back to here. And we observed also, in terms of the complexity of this algorithm, at most, you can see from either version, if you look at the iterative version, the number of iterations is at most log y. And where does that come from? Y is the exponent. So why do I say log y steps here? Yeah?
Probably because we'll be splitting y in half for each iteration.
Okay. So in the recursion, you're splitting y in half each step. So that's why recursion is. In the iteration, you're looking at each bit of y. And there are log y bits in y. So that's the number of steps. And log y, we know that y is less than or equal to n. So log y is less than log. It's going to be less than log e big N. And then the operations that you're doing, the squaring and the division and the multiplication, those are dependent on the length of n. So there's little, if n is a number of bits in big N, those would be n squared, little n squared operations. And log y is, I said, less than log big N, which is, we're going to call little n. So it all goes together as n cubed. So remember, you got to distinguish between the number itself, which is big N, and the number of bits in it, which is log of big N, which we're denoting as little n. So it's an n cubed, where n's a number of bits operation at worst, which isn't the fastest thing in the world, and in fact is a problem with RSA. RSA, the encryption step, does a modular exponentiation for giant integers, and those integers get longer over time as computers get faster, as we'll discuss, and becoming sort of a bottleneck. More to say about that later. All right, another thing that RSA uses is it needs to find greatest common divisors. And the neat thing about this is this algorithm for greatest common divisor was due to Euclid and is over 2,500 years old. So that algorithm that was discovered by the ancient Greeks is key to modern e-commerce. So just to remind you, it's a GCD of two integers is the largest integer d that divides both of them. So let's just practice. What's the GCD of 14 and 6? Okay, 2. They're both even, so it's at least 2, and there's no bigger one that divides them. What about 50 and 17? Yeah, that's 1. What about 12 and 20? 4. Okay, and here's the algorithm. It's very simple. One way to state it is right here. If b is 0, you could also write it iteratively, but if b is 0, then the greatest common divisor is a. So if we're trying to find the greatest common divisor of 7 and 0, the answer is 7, because 7 divides 0 as well as 7. Otherwise, we make a recursive call in GCD, and the old second parameter b becomes the new first parameter, and then the new second parameter is a mod b. So let's look how that pans out for 14 and 6. So GCD of 14 and 6, what's the recursive call going to be?
GCD of 6.
Okay, so it's going to be the GCD of 6 and 14 mod 6. So what is 14 mod 6? 2. Divide 14 by 6, 2 is left over. So you get GCD of 6 and 2. So what does that become? The GCD of 2 and 6 mod 2, which is 0. And that's the base case, so the answer is 2. So you just keep it. So you can easily see how you can turn this into a loop. Okay, what about 50 and 17? There you got to do the remainder in your head. So let's see, 17 times 2 is 34. 16 would be the remainder. So you get GCD of 17 and 16. And that turns into the GCD of 16 and 1. And that turns into the GCD of 1 and 0. So we get an answer of 1. Okay, and then 12 and 20. What's going to happen there? What will the first parameter be? 20. And what will the second parameter be? What's 12 mod 20? I heard an 8 and a 12. So we take 12 mod 20, And yeah, the modulus is 12. You know, a couple ways to look at it. One is that 12 is already smaller than 20, so there's really nothing to do. It's just automatically 12. So this shows you something. If you start out with an A that is less than the B, it just flips them, the first step. And then once you've got that set up, all the rest of the steps, A will always be bigger than B. Or equal to, I guess, is possible as well. So from 20 to 12, where do we go? and 8. And then 12 and 8 is going to go to 8 and 4. 8 and 4 is going to go to 4 and 0. So the answer is 4. Now, if someone were to ask you on an exam, what's the GCD of 12 and 20? I wouldn't recommend using the algorithm. All right? It's easy enough just to do it by inspection. You say, okay, what's the biggest thing? It must be 4. You know, if you're no good at that, you can use the algorithm. But a lot of times for small numbers, it's simpler just to figure it out. Like, for example, 50 and 17. You know 17 is prime and 50 isn't. 50 is not, well, more to the point, 50 is not a multiple of 17. So your GCD is going to be 1. Okay, so that's GCD. Any questions I can answer about that? We're going to talk about it a little bit more here, but that's the algorithm. Euclid didn't actually describe the algorithm in terms of mod. He described it in terms of subtraction. So what he said was that this step down here, GCD, instead of B, A mod B, he said B, A minus B. So we know that division, that mod is just sort of repeated subtraction, so it amounted to the same thing. It took more steps, but you end up in the same place. Okay, and there, in fact, are the two versions, the recursive version and the iterative version, which work basically the same way. This is what I just mentioned, Euclid's rule, what had to do with I'm wondering if I wrote that backwards, but I guess it doesn't matter. Anyway, Euclid did it with subtraction instead of repeated subtraction instead of taking mods. And there's a little proof here. I'm not going to go through it. It's pretty straightforward. If you're interested, you can check it out. That's Euclid's proof of the correctness of his rule. Basically, he showed that those two GCDs are the same by showing that each is less or equal to the other. Therefore, they must be equal. I'm more interested in complexity here. How long does it take? If you've got n-bit numbers, how long is it going to take to compute their GCD? We want to make sure this is efficient enough. So first we'll start with an observation that I'll prove. That is that if A is greater than or equal to B, then A mod B is less than half of A. So why should that be true? Why should the GCD of A and B, I mean the mod, why should, when we take A mod B, where A is greater than or equal to B, why should that be small? Why can't it be close to A? Why does it have to be less than half of A? Yeah?
Because we know A is greater than or equal to B.
Well, okay, we know A is greater than or equal to B, but what does that, okay, continue.
So when you find the mod, then sorry.
Okay, well, no need to apologize. Yeah?
If the number you're removing is less than half of A, remove multiple times.
Okay, so suppose B is tiny, okay, compared to A. What's A mod B? What do you know about A mod B? A mod B is going to be less than B. So if B is tiny to start with, A mod B is going to be tiny, right? Right? If b is 3, we know the answer's got to be 0, 1, or 2, no matter how big a is. Okay? So if b is small, that implies that a mod b is going to be small. But what if b is big? What if b is close to a? Yeah.
I mean, A mod B is A minus B.
Right, in that case, a mod b is just going to be a minus b, and if a and b are close, then the difference is going to be small. That's the intuition behind it. Either b is not close to a, in which case the modulus is, the modulus is always less than b, but if b is not close to a, then the modulus is going to be less than b, which is not going to be close to a. On the other hand, if b is close to a, then the modulus is going to be the same as their difference, and that is going to be small. This spells it out. So suppose b is less than equal to half of a, then it's going to work out that a mod b is less than b, which means that a mod b is less than a over 2, because b is less than or equal to a over 2. On the other hand, if b is greater than a over 2, then the modulus is just going to be the difference, and the difference will be less than a over 2. So either way, you can show that it's less than a over 2. You might have to sit and stare at this a while to get the particulars, but the intuition is either b is big, and as a result the modulus is small, or b is small, and as a result the modulus is small. So what that means is that this puts a bound on how long the algorithm can run, because that modulus keeps getting smaller. So here's the analysis over here. I'm saying that at most every other I like how I wrote that. Every other repetition, I'd like to say that every repetition a is cut in half, but why can't I say that? Yeah.
Sometimes you have to.
Sometimes what?
You have to switch them.
Sometimes you have to switch them. So we know that when we make this recursive call, that a mod b right here is going to be less than half of the original a, but it's not a yet, right? So it may be that in this the next recursive call, a mod b and b switch positions. So that's why I'm saying at most every other repetition a will be halved. Maybe it's not halved every time, but every other repetition. So maybe in the second, the fourth, the eighth repetitions, it's going to be halved. And they're going to be at most 2 n repetitions. How do I know that? Yeah?
Because after 2n repetitions, one of the numbers will be 0 and you get your answer.
Yeah, that is true, but also what it follows directly from that first statement is a is halved. Basically, every other repetition, a loses a bit. It's halved, so it loses a bit. So eventually, it's going to go to 1 as well. So that puts a bound on the number of repetitions. So you've got 2 n repetitions. Each repetition, you're doing a mod, which is an n squared operation. So it's n cubed. O of n repetitions, each repetition is O of n squared. The algorithm is O of n cubed. Okay? Turns out that's an overestimate. It is O of n squared, but actually there's a tighter bound. But we'll talk about why the bound can be made tighter. We won't derive it, but I just want you to see why it's O of n cubed. Each step you're doing a mod. That's the n squared operation, and you've got at most 2 n steps, because every pair of steps you're guaranteed a's to be cut in half. So what are some reasons why that our analysis was a little bit sloppy? Do you think of some reasons why it could be faster than n cubed? Yeah?
The mods get smaller as you go.
Okay, so we're using n to stand for the length of the numbers. But they get smaller as you go. Each repetition, n is getting smaller. So yeah, the first mod will be n squared. The next one is really going to be n minus 1 squared or something. Anyway, they get smaller and smaller. So that's one source of overestimate. The numbers aren't the same length all the time. The modulus goes down, so their length goes down. What's another reason? What about a statement that every other step A is halved? Yeah.
That's technically only true at least once, because once you swap them into the right place, every one after that will be fine.
Right. You remember when we were looking at, before we started this analysis, I observed that, like, if you take the mod of 8 and 12, yeah, they get swapped to mod of 12 and 8. But thereafter, there's no swapping that happens. A is always bigger than B. So really, instead of saying every other time A is halved, we could just say almost every time A is halved. A is halved every time except possibly the first time. So that's another source. And then there's a third source, which is, yeah, A is at least halved, but a lot of times A may be more than halved. Right? The halving is sort of a worst case possibility. So those are three possibilities for the overestimate. In reality, A is essentially halved every time. Some of the times it's actually more than halved, and the numbers, meaning the length of the numbers, get shorter over time, so those mods get faster. So it turns out that Euclid's algorithm is n squared. And the turns out also the worst case is for if you take trying to find the GCD of consecutive Fibonacci numbers. It's kind of a neat little thing. So remember Fibonacci numbers, the first one is 1, the second one is 1, and the kth one is the sum of the two previous ones. So they go like 1, 1, 2, 3, 5, 8, 13. It's harder for me to do it in my head after a while. 21. Anyway. Those are the Fibonacci numbers. And let's see what it looks like when you take their GCD. So if you take the GCD of the kth Fibonacci and the k minus 1 Fibonacci, there it is. I just applied the rule. So the GCD of f of k minus 1, of f of k and f of k minus 1 is the GCD of f of k minus 1 and f of k mod f of k minus 1. I just applied the rule there. F of k we know is the sum of what did I do here? Oh. It turns out that f of k minus 1 is slightly more than half of f of k. So we can replace the modulus with a subtraction. And then we know that f of k here is the sum of f of k minus 1 and f of k minus 2. So I just make that rule there. How's that going to substitute? Simplify, rather. How's this subtraction going to simplify? Right, f of k minus 1, those are going to cancel out, and so we're just left with that. So it turns out that the GCD of k and k minus 1 Fibonacci numbers is the same as the GCD of the k minus 1 and k minus 2. Okay, which means the next step will be f of k minus 2, comma, f of k minus 3, and so on until you get down to that step. You get the answer of 1. So I haven't proven, but what I've proven here is the GCD of any two consecutive Fibonacci numbers is going to be 1. It turns out that's the worst case in terms of number of steps it takes for n-bit numbers. Just which really has no pertinence to where we're headed. It just thought I'd mention it. Yeah?
So for the first and the third bullet point on the left-hand side, what if that only reduce it by a constant?
Say that again. We're talking about this?
Or on the left-hand side, the bullets, the A is half almost every time, and or the short over time. Wouldn't that only...
This would only change it by a constant, yeah. It depends on if it's, I guess if we could show that it was, say, on average it was cut in a quarter, that's still just going to be a constant. So I guess this is the real answer. That's the real reason, because the numbers get shorter each time. The numbers get shorter by a bit each time, so. Anything else? All right, so that was GCD. Another algorithm that is used by RSA is modular multiplicative inverse. So if we have a number A and we want to know its modular multiplicative inverse, mod n, we're just looking for something we can multiply it by to get 1 mod n. So it's sometimes written as a to the negative 1 mod n. Or sometimes it's written as, solve the equation, ax is equivalent to 1 modulo n. So for example, what can you multiply 2 by to get 1 if you're working mod 3? In other words, what's the modular multiplicative inverse of 2?
2.
It's 2. 2 times 2 is 4, 4 mod 3 is 1. It's not 1/2. We're always working with integers here. So the answer is 2. Okay, here's another one, the inverse of 4 mod 7. So the way to think about it is, think of a number you can multiply 4 by and get an answer that is 1 more than a multiple of 7. That's how you do them in your head when the numbers are small. And in any event, you don't have to, even if you need to do it with paper and pencil, you only need to consider what are the possible values, what are the possible, a priori, what are the possible inverses of 4? What numbers do you have to consider?
Numbers less than 4.
Not less than 4. Less than 7. 0 is never going to be the inverse of anything. 0 doesn't have a multiplicative inverse, mod anything. 1, the only thing it's the inverse of is itself. So really, the only numbers that are candidates are 2, 3, 4, 5, and 6 in this case. Only 5 numbers. But in any event, what can you multiply 4 by to get something that's 1 more than a multiple of 7? 2. 2 times 4 is 8. 8 mod 7 is 1. So the answer is 2. What about that? The inverse of 5 mod 8. So you can't multiply anything, by 5 to get 9. That's 1 more than 8. What about to get 17? No. 25 is 1 more than multiple of 8. 5. 5 times 5 is 25. That's 1 more than 24, which is multiple of 8. So 25 mod 8 is 1. So 5 is its own inverse. 9 mod 11. Okay, it's getting harder now because there are more numbers to consider. We've got to go 2 through 10 of the possible inverses. Fortunately, it's easy to multiply 11 in your head. Okay, so what's the answer? Okay, so 5 times 9 is
45.
45. And 11 times 44 is a multiple of 11. Okay? So 5. Now, we're about to study an algorithm for computing modular multiplicative inverses. But I got to say that, say on the final exam, I'll give you a question which is to find the modular multiplicative inverse using something like this. You're much better off getting good at doing it in your head than at trying to follow the algorithm we're about to study. Because it is really easy to make mistakes in that algorithm. And it takes a long time to grind out the answer. It's a lot easier just to sort of look at it, consider the 3 or 4 or 5 possible answers, and figure out which one it is. Okay, this one, we talked last time that numbers do not always have an inverse. So it turns out that 4 to the negative 1 mod 6. 4 does not have an inverse. Let's just make sure. 4 times 2 is 8. 8 mod 6 is not 1. 4 times 3 is 12. 12 mod 6 is 0. That doesn't work. 4 times 4 is 16. That's no good. 4 times 5 is 20, that's negative. So that, there's no inverse in that situation. Now, is that unusual that a multiplicative inverse doesn't exist? What about in the real numbers? Does every real number have a multiplicative inverse? Most of them do. I can think of one that doesn't. Which one doesn't have an inverse? 0. So you're used to that. What about the integers? How many integers have multiplicative inverses? Anybody want to take a stand here? Yeah?
It's like 1.
Okay, you got to vote for 1. Anybody got a different opinion? No, you changed it to 2. All right, so what are the 2? 1 and negative 1. 1 is its own inverse, negative 1 is its own inverse. No other integer has an inverse. So don't think it's odd that we got this mathematical system where some things have multiplicative inverses and some don't, because the ones you're most familiar with, that's true there as well. Here's how you tell. The inverse exists if and only if A and N have a GCD of 1. Another term for that property is called relatively prime. So A and N are relatively prime if their GCD is 1. A will have an inverse mod N if and only if A and N are relatively prime. So you can see for all the ones except the last, the GCD of 2 and 3 is 1, the GCD of 4 and 7 is 1, 5 and 8 is 1, 9 and 11 is 1. But the GCD of 4 and 6 is not 1, it's 2. So you can just tell from the GCD computation that there's no inverse in that situation. All right, now we're going to dive into an algorithm for computing modular multiplicative inverses. And we're going to start with this fact. This kind of just comes out of left field, but if D divides both A and B, and you can contrive to write D as AX plus BY for some integers X and Y, then D is the GCD of A and B. Right? That seems like a useless fact, but it turns out to be key to our algorithm for computing inverses. So let's look at some examples. Let's let A be 8 and B be 5 and D be 1. Now we know that the GCD of A and B is 1. So that means that we should be able to construct, find an x and a y such that AX plus BY equals 1. And in this case, we're working over integers, no modular arithmetic. So what x and y will work to add, so that AX plus BY would be equal to 1? Obviously, we've got to use some negative numbers here. What's that?
Negative 3
Negative 3
and 5.
and 5? Let's see. I use negative 3 and 2. The numbers don't have to be unique. But let's see. Just negative 3 and 2. Well, I hoped I'd worked out the math. So if you use x is 2, so 2 times 8 is 16, and negative 3 and 5 is 15. Add those together, you get 1. So yeah, I don't think negative 5 would work. Okay, what about these? 30 and 16 have a GCD of 2. What's an x and a y that work? What should we multiply 16 by? Remember, we're trying to end up with a 2. 2. All right, if we multiply 16 by 2, we get 32. And then so that's our y. Then if we let x be negative 1 and put them together, we get 2. So y can be 2, x can be negative 1. And the proof isn't difficult. Since D divides both A and B, so D is a divisor of A and B. So it has to be less than or equal to the greatest divisor of A and B. So that first statement is true just from the nature of what GCD is. Any divisor of A and B is going to be less than or equal to their greatest common divisor. Okay? Next step is GCD of A and B is a divisor of both A and B, right? It's a common divisor, so it divides them both. That means it must divide this AX plus BY. Why is that? How do we know it will evenly divide AX plus BY?
AX and BY are multiples of X and Y.
Yeah,
Or
because AX and BY are multiples of X and Y. So we know that GCD of A and B will divide AX and it will divide BY. So we'll divide the sum. And that means that the GCD of A and B is a divisor of this thing. So why do we conclude that GCD of A and B is less or equal to B then? I'll remind you, the GCD of A and B divides this thing. So that's the same as D. It divides D. And if something divides D, it can't be bigger than D. So anyway, we end up by showing both of these that shows that D and GCD of A and B are the same. Okay, so what? What good is this? Okay, so that's what we're starting from. So suppose we would like to find the inverse of A mod n, and we know that A and n have a GCD of 1, which means that an inverse exists. That's good. I say that all we got to do is find x and y such that ax plus ny is 1. Now, how do we know that x and y exist? How do we know we're going to be able to find an x and a y such that ax plus ny equals 1? Yeah.
We've already determined that the GCD of A and n is equal to 1.
Right. We're assuming the GCD of the, we're only doing this when the GCD is 1, so that's our B right there. So we know that there's going to be an x and a y such that ax plus ny is 1. Now, look at that equation and tell me, if you could find x and y, how could you pull the inverse of A out of that equation right there? This is where we're going to have to go back to modular arithmetic. Yeah?
Is it equal to X?
Okay, it is equal to x. The inverse of A is x. How can you show that? So before we go there, I just want to point out that we wanted to find the inverse of A mod n, assuming they have a GCD of 1. That implies there's going to be an x and y that makes this equation here work. And it turns out that that x that makes the equation work is the inverse of A mod n. But how do you show it? Yeah?
We know that ny mod n is just 0.
Okay, ny mod n is going to be 0 because it's a multiple of n. Okay, so someone else tell me what do we do with that? Yeah.
Well, then AX is equal to 1, and so you know that
Okay.
one of those is going to be
So basically, just take the mod, both sides of the equation mod n. So what's the right side of the equation mod n? 1. What is the left side of the equation mod n?
ax plus 0.
Right, ax plus ny mod n simplifies to ax plus 0 mod n, because ny is 0 mod n, because it's multiple of n, which is ax mod n. So if you take both sides of the equation mod n, you're left with ax on one side and 1 on the other, mod n. So ax is the same as 1 mod n. Ergo, x is the inverse of a. So what this means is that if we had a way of finding the x's and y's that make equations like this work, we would have a way of finding inverses. We would just use the x. So the algorithm we're about to see for computing modular multiplicative inverses, really what they do is they compute the x and the y that makes those equations work out. And then you just use x as the answer. So let's take a break and we'll see how such an algorithm works. All right, so what we're going to look at now is an algorithm that will, we can give it the a and the x, or sorry, the a and the n, and it can give us back that x. We'll also compute the y. We don't care about the y. Oh, well, I guess I should have demoed this first. This is just showing you the idea behind it. So if we want to compute 3 to the negative 1 mod 13, it turns out that we have to find x and y such that 3x plus 13y is 1. Okay? So our goal is to find the inverse of 3 mod 13. So we set up this equation. What's the, what x and y will work? Negative 4 and 1. Okay, that's what I say. But again, I don't think these are necessarily unique. I'm not sure. Okay, so what does that tell us is the inverse we're looking for? Remember, we're looking for the inverse of 3 mod 13. So based on what we just found, x negative 4 y 1, what is the inverse? Negative 4. But I'm asking, I want an answer between 0 and the modulus. So I don't much like negative 4 as the answer. But you just take, if negative 4 works, anything that's equal to negative 4, mod 13 will work. So what would be sort of the standard form to say is the inverse? 9. So very often, maybe always, you get a negative number out of the algorithm we're about to look at. So the last thing you want to do in order to put it into the range that I like is to, typically it just works to add the modulus to it. But formally, you want to take the inverse mod 13 and use that as your answer. So I prefer 9 as the answer to negative 4. So here's the idea. It's an extension of Euclid's algorithm. So that's the good news. It's not, it's not a horrible algorithm, but it's, there are a lot of details in it. And that's why I say if you try to simulate it on paper, you're almost certainly going to make a mistake. I always do. There's just a lot of things to keep track of. So the algorithm, you see, if you ignore, well, let's look at it. You're taking EE of A and B, so extended Euclid. If B is 0, you return 3 things. So if the thing is square brackets, you think of it as an array of 3 integers, or you think of it as an object that contains 3 integers, or whatever. A triple of some kind. So there's 3 things. If you look at the first thing that's being returned, that's the thing you would return normally from Euclid's algorithm. The base case, the GCD is 1. So that's the 1. And then we got the 0 in the A. Otherwise, what you do is oh wait, I just said a lie. Got a wrong. A is what you normally return. When you take the GCD of A and B is 0, the GCD is A. So the third thing is actually the GCD. So that's a GCD and that's a GCD there. So the first 2 things are the x's and the y's are computed. So we're souping up Euclid's algorithm to find x and y as well as the GCD. In the recursive case, we're going to get 3 things back. We recursively compute the GCD of the EE of B and A mod B. We get back x prime, y prime, and d, which is the GCD. And we have to sort of mangle them to get the thing we return to whoever called us. So whatever d was gets returned directly. So you can see this thing is, the third thing in the triple is just the GCD. It's returned all the way up. Whatever the second thing in the triple was from the recursive call becomes the first thing in the triple here. And this is how you compute the second thing in the triple. This is where it's easy to go wrong. You've got to do an integer division of A and B, throw away any remainder, multiply that by the y prime you got, and then subtract that from the x prime you got. And it just turns out that, when this percolates up to the end, you'll know x and y and d. And then you can use whatever x you get back, you throw away y and d. Well, I guess you don't throw it away. If d is 1, you have found an inverse. If d is not 1, you've discovered there is no inverse. And the inverse is just x, which you compute, you normalize it with x mod n. So, it's a mysterious algorithm. I haven't explained why it works. It's a little detailed with all the integer operations you're doing, so it's easy to get wrong. But let's try to trace through how it works. So let's say we're going to compute extended Euclid of 3 and 13. What recursive call will be made? So you're looking at that top box there. B is not 0, so what's the recursive call that's going to be made? What's that? Yeah.
Extended Euclid will be called, and it will be 13 and 3.
Right, 13 and 3. So it's the same as GCD, except you get 3 things back instead of 1. So If we did GCD of 3 and 13, we would turn around and the recursive call would be for GCD of 13 and 3. And we make that recursive call, we're going to get back x prime, y prime, and d. And then we'll use that to decide what we return. Well, we don't have a x prime, y prime, and d yet. Let's look at the recursive call, EE of 13 and 3. What recursive call is it going to make? Yeah?
3 and 1.
3 and 1. And it'll get back its own x prime, y prime, and d and do something with it. But let's look and see what 3 and 1 does. What recursive call is it going to make? Yep.
1 and 0.
Yep, 1 and 0. And there it is. And that's the base case. So you can see that we've got 4 stack frames on the stack. We've got to compute the answer to this. And we'll return the triple up to this invocation, which will figure out what to return to that invocation. We'll figure out what to return up there, which will figure out what to return over here. So what's going to be returned? What triple will be returned by that base case there? Here's the base case. So 1, 0, 1. That's what gets returned. Now let's make sure this works. Right? So this claims that, that's an x and a y and a d, and we know a and b. A and b is 1 and 0. So it ought to be the case that 1 times 1 plus 0 times 0 equals 1. That's what the algorithm is supposed to do. So the base case do the right thing here? Yeah. 1 times 1 is 1 plus 0 times 0. And that's just ax plus by. That's 1 and it's equal to d, which is 1. So we're good. And a proof that this is correct would, that would be the base case of the proof, basically. So it would be an inductive proof on the length of the recursion. And we would do the base case there, the way I showed you. So that triple is returned to this other invocation up here. And in the context of this stack frame, x prime is 1, y prime is 0, d is 1. That's what was computed down here. Now, here comes the hard part, do in your head. What does it return? What does EE of 3, 1 return? Here's the formula. So what's the first thing in the triple going to be? It's going to be the 0 here, the y prime. And what's the d going to be? That's easy. The d is always the same. That's 1. Place you go wrong is computing this, just because there's a lot of symbols flying around. Let's see if we can do it. X prime is 1, so it's 1 minus. What's a divided by b? 3 times y prime. Oh, okay, that's easy. So it's 1 minus 0. Even I can do that. So it ought to be 0, 1, 1. Is that what we decided? Yeah, great. And we could do another check. In fact, let's do it. That purports that, it should be the case that a times x plus b times y is equal to 1. So let's see, 3 times 0 is 0. 1 times 1 is 1. That's equal to 1. So that's the invariant we'll see all the way up. Okay, great. Now what's going to get returned? Well, let's see. It's going to, the y prime, the first thing will be y prime, which is 1. The last thing, b is always 1. And then we're going to take x prime, which is 0 minus 13 divided by 3 is 4. So 0 minus 4 times 1, negative 4. 1, negative 4, 1. And again, you could do the ax plus by check here. That should work out. So that gets returned up to there. Make a long story short, if we did this again, we would get negative 4, 1, and 1. So that gets returned here, we're trying to do the inverse of a and n, so we computed this. And since we're getting back -4, 1, and 1, we know d is 1, which means the inverse exists. So we just pick out x, which is -4. And we take it mod 13, which turns it into a 9, which is what we return. Oops. Okay, I'll stay on this page since I can't get back. Hold on. There we are. Okay, now, do you understand now why I say that if you're sitting in an exam and you're supposed to compute the inverse of 3 mod 7, that you should not use this algorithm? You should just think 3 times 5 is 15, that's 1 more than 14. The answer is 5. Okay? It's really a sad side. I've seen this happen a lot. People just furiously working this through with the final together. Okay. Now, this is the proof of correctness, and I'm not going to go through it. It's basically a inductive proof on the depth of recursion. So the base case of the induction is base case of recursion, and you show that if the recursive call is correct, then after you rearrange the numbers and return them, they'll be correct as well. It's not deep math, it's just details with integer division and mod and such. So if you'd like to dig into it, feel free, but I'm not going to hold you to it. Okay. So that is how you find modular multiplicative inverses. Now, next thing. We're almost done with the recipe for RSA. We almost got all the algorithms we need. Turns out that the key to RSA is it needs to be able to efficiently determine really long prime numbers. And by really long, I mean like 1,000 bits or 2,000 bits or 4,000 bits or something like that. So not particularly long from, it's not like you're setting world records for finding longest prime numbers, but you need an efficient way to find 1,024-bit prime numbers quickly. That's what RSA depends on. So we need to worry about prime numbers. So just to remind you, a prime number is an integer greater than 1 whose only factors are 1 and p. So it's an integer p greater than 1 whose only factors are 1 and p, 1 in itself. So the primes start out 2, 3, 5, 7, 11, and so on. And the other numbers greater than 1 that aren't prime are called composites. And back in, I don't know how long ago this was, but there was, people were wondering at some point, mathematicians were wondering, is there a largest prime number? If you got to a certain point, could it be the case there are no more prime numbers beyond that? You could, if you didn't know, you would wonder. And the proof is actually fairly simple. So let's assume, we're going to do a proof by contradiction, assume there are only k prime numbers. And we'll just name them p1 through pk. K could be large, but let's assume there are a finite number of prime numbers. And then let's compute this, let's multiply all the prime numbers there are together and then add 1. That gives us a new number. Now I claim that P1 is not a factor of this thing here. What would be the argument that P1 does not evenly divide Z? Yeah.
We have to divide 1 and the product on the right.
Yeah, essentially. So if you think about what would happen if you divided this thing by P1, what would the remainder be? It would evenly divide this chunk, and there would be 1 left over. So you divide this thing here by P1, the remainder is 1. You divide it by P2, the remainder is 1. It's just constructed, so no matter which of these primes you divide it by, you get 1 as the answer. It'd be like multiply 3 times 5 and add 1, you get 16. 16 divided by 3, remainder is 1. Divided by 5, remainder is 1. So what does that tell us about this number? The fact that it has, none of these prime numbers are divisors of it. What does that tell us about Z? Yeah?
It's either prime or it has a prime factorization that doesn't include the.
Right. The only two possibilities is this number is itself prime, or it's divisible by primes that aren't on the list. Either way, that's a contradiction of our assumption if there were only k prime numbers. There has to be more. So there are an infinite number of prime numbers, which is actually good news for RSA. If there were only a finite number, that could pose problems. So we're interested in generating prime numbers with n bits. And the way we're going to do that, and we need to get them at random. We need to be able to choose prime numbers at random of a given length. So the general idea is we're going to get a 1,000-bit prime number, we're just going to randomly generate 1,000 bits. That gives us a number of the right length. Then we're going to test it to see if it's prime. If it is, good. If it isn't, we'll randomly generate another prime number and test it until we find one that's prime. So the problem now is, how do you test an integer to see if it's prime? Yeah?
Test all like prime numbers below it.
Okay, so one thing would be to, when you say test all prime numbers below it, you mean, the problem is that the list of all the prime numbers below it, coming with that list is difficult.
Yeah.
Yeah?
We could check everything from the square root of the current number below.
Okay, what's called trial division. You basically see, can I divide it by 2? Can I divide it by 3? Can I divide it by 4? And so on. You only have to go up to the square root of the number. But that doesn't work too well simply because there are too many divisions to do. So one possibility is to factor it. Unfortunately, there's no known efficient algorithm to factor numbers. Factoring has escaped us so far. In fact, if someone were to discover a fast factoring algorithm today, e-commerce would collapse tomorrow, because all of our the encryption is the security of RSA encryption, which is the basis of our current e-commerce system, is founded on the assumption that factoring is hard. A fast factoring algorithm would destroy RSA. So a lot of people are hoping that there isn't a fast factoring algorithm. Okay? So another possibility, rather than trying to factor it, is to do trial division by every integer from 2 up to the square root of p, like we just mentioned. That just requires too many divisions. It requires at least the square root of p divisions, which doesn't look too bad. That's just a polynomial. But remember, we're interested in p is a big number, but it has just a small number of bits, 1,000 bits. So instead of, we need to express the complexity of what we're doing in terms of the length of the number, not in terms of the number itself. And p is on the order of 2 to the n. If n's the number of bits in p, it's going to be roughly 2 to the n. So this is the more honest way to look at it. It takes 2 to the n over 2 trial divisions. So in other words, if n is if you want a 1,000-bit number, it's going to take 2 to the 500 trial divisions. And that is just an unimaginably large number. Right? The universal, whatever happens to the universe in the end, whether it collapses back on itself or diffuses to nothing, we wouldn't be done by the time that happens. So that's not going to work. Now, in 2002, there were 3 computer scientists in India, a professor and 2 undergraduates, that discovered the first known primality test. That was polynomial time. And it started out being n to the 12th. And then after people looked at it for a while, it got simplified to n to the 6th. So there is a polynomial time test for whether a prime number is, whether a number is prime. But it's too inefficient to use in general. So that's not actually what's done either. In practice, what's used is a probabilistic test. And I'll explain what I mean by that, if I can, in 5 minutes. This is a famous theorem from number theory, Fermat's little theorem. And it says that if p is prime, then if you compute a to a p minus 1 mod p for every a between 1 and p, you'll get 1. So let's let p be 5 and see what we get. So if we take 1 to the 4th mod 5, that's 1. 2 to the 4th mod 5 is 16. Take that mod 5, you get 1. 3 to the 4th power mod 5 is 81, you get 1. 4 to the 4th mod 5 is 256. Take that mod 5, you get 1. So it all worked out. You take 1, 2, 3, and 4 to the 4th power, 1 less than the p, you get 1. Now let's try it with some number that's not prime. Well, if you take 1 to the 5th mod 6, you get 1. But if you do 2 to the 5th, you get 2. 3 to the 5th, you get 3. 4 to the 5th, you get 4. And 5 to the 5th, you get 5. So Fermat's little theorem, if it's prime, all these are guaranteed to be 1. If it's not prime, it doesn't say anything about it. There it's 1, but the other places it isn't. So Fermat's little theorem, 1640, so almost 400 years ago, what people would have called an interesting little theorem about prime numbers, but of no practical importance. I can hear the politicians saying it. We appropriated, $100,000 for Fermat to do mathematics research, and all they came up with was this thing that's totally useless. And it was totally useless until it wasn't. It's a key to modern encryption. It's how RSA finds prime numbers. It applies Fermat's little theorem. Now, can you imagine how you could use Fermat's little theorem to find prime numbers? Probabilistically, yeah.
You could check a large number of those exponents, and then if enough of them are 1, you can assume that it's
Yeah.
and then you can run the algorithm on it.
So here's the thing. Fermat's little theorem makes a guarantee up here. If it's prime, you'll always get 1 out. No matter what exponent you pick, if it's in range, you'll get a 1 out. But it doesn't make any guarantees about this guy. Okay? So, but we'll have to look at this in more detail another time. But the idea is that to test a number for primality, you just take the number, you apply this test to it from, say we randomly pick these numbers right here, raise it to the prime minus 1 power, the assumed prime minus 1 power, mod p, and see if you get 1. And you do that over and over again. And you do it enough times, if you keep getting 1, you keep getting 1, you keep getting 1, you figure, yeah, it's probably prime. So how does that make you feel? That the security of your Amazon purchase, the security of your credit card, is based on an encryption key that's probably right. And that's the truth. The good news is the odds, I can show you next time, the odds that it's not prime and that the encryption isn't either going to work or may not be secure, you can control the odds. And so you can choose a prime number with a certainty that it's wrong only in 1 time out of 2 to the 100, let's say. You can pick your exponent. Does that make you feel any better? That it'll only fail 1 every 2 to the 100th times. Right? I've got students, I've had lots of students that really don't like that either. The thing to realize is the odds that a meteor is going to strike the computer are much higher. The odds that a cosmic ray will flip a bit are much higher. So there are lots of ways computers can make mistakes. This is just another way. So we'll follow up on this next week.